welcome Professor Yonina Eldar to the Network Science Institute. Yonina is the Allen Chair Professor of Electrical and Computer Engineering at Northeastern. Before this, she was at Weizmann Institute. She was a professor there. Before that, was Technion. She has visiting professorship appointments at MIT, Princeton, the Broad Institute, Duke, Stanford. She's a member of the Israeli Academy of Sciences and Humanities, IEEE fellow, lots of awards. She won the Israel Prize in Engineering in 2025. For those of you who are in the US, that's equivalent to the National Medal of Science. Big deal. The Landau Prize, she was selected as one of the 50 most influential women in Israel. She was a member of the Israel Committee for Higher Education. She's the editor-in-chief of Foundations in Signal Processing. She has several influential books on compressed sensing and sampling theory. As of this morning, her H-index is 126. Take a moment, think about it, absorb it. And in particular, she has done groundbreaking work on sampling. So for those of you who know about the Shannon-Nyquist sampling theorem, she crushed it. She was like, no, we can be more efficient here. Whatever you're sampling has structure. And so she developed the theory behind sub-Nyquist sampling, which has had many applications across many different domains, from medicine to radar, communications, etc. And so we're very lucky to have her join our faculty here, and she's welcome.
Thank you. Of course. Well, okay, after that introduction, I feel like I shouldn't say anything because I could only, but thank you, Tina, for being so generous. And actually, this is a good opportunity to thank you widely. So since I arrived here, Tina has been just so amazing and generous. As you could hear from that introduction, which, most of it she, of course, amplified, is, she's just been walking around and promoting me everywhere and giving me these opportunities. So I can't thank you enough. And I'm really so excited. This is actually my first talk given here as being at Northeastern. So you're the guinea pigs, but I'm super excited for this opportunity. And I'm really excited to be here. And I'll say before I begin the technical part that hopefully you see how excited I am. So bear with me. But I'm really looking at this as an opportunity, besides sharing some of what we're doing, is really to expand and collaborate. And this particular institute is just so inspiring to me to see people from so many different backgrounds collaborating and finding a way to do work together. And to me, that's just so inspiring, even before I got here. And now that I'm here, seeing the environment and the people and the interaction. So I'm really viewing this as an open call to collaboration. And if there's anything here at all that looks interesting to anyone or something that you think could be relevant, then please feel free to reach out to me. Of course, ask questions throughout the talk, but also afterwards, I'm here and really happy to collaborate. So with that, I'll begin. So what I want to talk about today are some thoughts and how we could try and merge ideas of models that at least people like me, coming from signal and image processing, we always, before the deep learning revolution, always relied on models. How we can merge that with learning, right? Where our goal is really to get efficient networks, networks that could work on the edge, low power, to be accessible everywhere. So that's really the goal. Before I start with the technical part, I just want to say two words, since the goal really is beyond the technical part, is really collaboration. I want to say a few words about our broader activities. We're not going to go through all of them here today, but if there's anything in the broader activities that's interesting, I'm happy to talk offline or some other time. So at Weizmann, we started a Center for Biomedical Engineering where, let me see if I can get rid of this. Great. Where our goal really is to see how we could use signal processing and AI at the interface between engineering, health, sensing, and communication. So using technology to advance these different domains. And the center, basically, the point is to put together clinicians, people from a more mathematical background, engineers and scientists. And here it's done all the time, but in Israel a little bit less. So, part of the lab is focused, still we're in the math department, so on theoretical fundamental limits. Then we have the lab arm where we really build technology based on these theoretical ideas. We have the clinical arm where we look at health applications, and then in a more internal scientific arm where we look at how these ideas could have relevance to different scientific discovery. So on a high level, in the technology part, we look a lot at sensing devices. Tina mentioned sampling, so how we actually acquire signals, how we do that in an efficient way. We've, over the years, looked at a variety of different applications. So a lot of medical imaging, super resolution, a lot of remote sensing. Today, we're looking a lot at different communication systems, so next generation communication systems, radar systems, autonomous vehicles, of course, defense applications, combinations of sensing and communication. So this is all in the technology arm, where I guess the important thing for me, at least, to stress is that we really try to look at theory, but also how theory could be built in practice and impact applications. This is a more detailed version of a lot of the different topics, so I won't go through them, but you can get a sense of the types of things we're looking at in the technology arm. And then on the clinical side, we work a lot with clinicians, first to see where the things we're developing could have impact in medical applications, but also, of course, the reverse, to kind of understand what are some of the needs where we could potentially bring solutions. So just some of the more recent things we're doing, we're looking a lot at ultrasound. We'll talk about that a little bit in the talk today. Guided ultrasound, how to convert between modalities, how to combine modalities. We're looking a lot at wearable devices, so how to have remote efficient devices. We're looking at using, let's say, radar for medical imaging, for vital sign monitoring. So some of this we'll talk about, but just to give a sense of the broader interest. And we've been working with a lot of hospitals, both in Israel and actually in the Boston area. And of course, our hope is now that we're here to expand on that as well. So in a nutshell, what we're trying to do is to see how we could use signal processing and machine learning to really enhance performance of different technologies and to make technologies available everywhere, okay? So we want anyone to be able to use technology. We want it to be at the edge, close to the patient, low power, etc. But of course, this is very challenging, right? Because we want to be able to extract various different types of information in an efficient way, in a low power way, in a way that's robust across different applications. And this is really where kind of the model-based AI comes into play. So what we're trying to do is to see how we could build AI that's interpretable, that's efficient, by using learning, of course, but also using the basic models of physics and engineering that we have traditionally used and putting it together in order to achieve this goal. And this brings us to the technical part of the talk, which is focused really on what we call model-based deep learning. And of course, many people are working on this in our community as well. So as we all know, and definitely no need to motivate to this community, you know, we're in the midst of the deep learning revolution. Deep learning achieves the best performance in almost any application you could think about. We all use it all the time, right? I mean, at least I use ChatGPT. I'm sure everybody here does, or its equivalent. We use this in self-driving, speech-to-text, you know, many, many, many different applications. We could do useful things. We could do crazy things like, you know, generate fake art, fake faces, whatever we want with generative AI. But of course, all of this comes with a price, right? So first of all, we need very, very large training sets to get good performance. The training can be computationally super demanding. And again, this is fine if you're, you know, Google or NVIDIA, but if we're thinking about the applications we're thinking about are on the edge, right? You know, individual users, medical conditions that are not prevalent, right? So here, that would not be relevant. Of course, interpretability is a huge issue, right? So we get an answer, you know, how do we know why that answer was made? And again, if it's just identifying a face, maybe that's less important. But if it's a disease, then, you know, if you're going to your doctor, you don't want them to just say, well, the network gave me this answer, you know, this is what it is. So interpretability is very important. Robustness and generalization. So I think, you know, we're all familiar with those examples where you train and you get very good results in hospital A, but you cross the street to hospital B and nothing's working anymore. So we're all familiar with this. And of course, it's all tied in together with the complexity. So, you know, GPT-4 uses 100 trillion parameters. Honestly, I don't even know what that means. Like, how do you imagine trillion parameters, right? It's just a number, like it doesn't mean anything. And clearly with so many, sorry, right? That's, you know, I'm a simple person, right? So I can't count that big. So, you know, clearly something that's using so many parameters is going to have amazing performance, but trying to get interpretability out of that, right? Trying to control that is going to be very difficult. So we want to take a different perspective, right? So if we stop and think about, okay, so what do people used to do in these types of applications? Well, people use signal processing. And the nice thing about signal processing is that it's based on models, right? So we start with a model. The nice thing about a model is that we can incorporate whatever we know, right? If we have domain knowledge, we have structure, we have constraints, we know how to incorporate that in a very structured way. The advantage, of course, is that we could get inference from small amounts of data, typically even one data point, right? Like standard signal processing works on one single input. And we also have nice techniques to assess the quality, right? So we could even know in advance how well we're going to do and whether or not it's even worth going through the motion or what SNR we need, et cetera, right? So everything is really nice and clean. Okay, so what's wrong with that? Well, of course, it requires knowing a model, and in complex settings, having an accurate model, of course, is not going to be practical. And the other thing is that the inference could be very slow, right? So even if we have everything is optimal and I could set up a differential equations with 150 unknowns, but then actually solving it is going to be very problematic. So these are probably, the two most common drawbacks of standard signal processing. And really what we're trying to do, and I'll try to talk about in the talk today, is see how we can merge those two things, okay? So we want to use the models, we want to use the knowledge, but we also want to use the power of learning. Okay, so how could we do that? So what I'm going to show now is just a really, really kind of very, very abstract, high-level view of signal processing and networks, and then we'll see kind of, visually how we could combine them. So in a standard signal processing problem, you start with your measurement. We're going to call it Y. So let's say Y could be a blurry image, or Y could be the output of some communication channel. You have some desired output that you actually want that we're going to call X. So that could be the clean image or the actual bits that were sent over the channel. And you have a model, right? That's why it's model-based. So in advance, we assume that we know or approximately know a relationship between our measurement Y and our output X. Okay, so we have some known function G. We know in advance that Y is approximately G of X. Okay, and G could be as complicated as you want, but it's a known model. And then what we do is we seek the value of X, right? We solve an optimization problem where we say we're going to look for the X that after it goes through G is going to bring us as close as possible to Y. And we may add regularizers and other things to that, but that's kind of the basic principle. Okay, so once we have that, we could decide whatever our metric is, right? It could be a norm, it could be something else. We're going to try to optimize that. And typically, especially if G is complicated, this is not going to have a closed form solution. So we'll end up with an iterative algorithm, which depends on the solver that we chose, right? Depending on the optimization solver that we chose. But they'll all have kind of the same framework. We'll have some pre-processing, we'll have post-processing at the end. And then in between, we're going to have this computation where part of it is going to be generic that just comes from the model, that generic that just comes from, let's say, the gradient, and then part of it is going to depend on the actual model. Okay, so this is where we have to know the model. And you iterate enough times, right, typically thousands of times, and you'll get potentially to the correct solution. Okay, now what happens in deep networks? Of course, the situation is very, very different. So in learning, we start with paired, again, supervised learning, just to make things simple. We start with paired inputs and outputs. Okay, we have some fixed network that we decide on in advance. So it's not directly related to this G of X or any model because we don't assume there is a model. So we start with a fixed network. We use those paired inputs and outputs to train the network, basically to learn the weights in that network. And then when we put in a new measurement Y, we hope that miraculously, right, we're going to get a good output X. Okay, so again, this is like a very, very abstract view of the two. Okay, so how could we combine them? So what we're going to talk about today, and of course there's many options of combining them, but we're going to talk about two main principles, focusing more on the first. So we're going to look at two approaches of combining them. In the first, which we refer to as unfolding, and we'll say more about that in the next few slides. Basically what we do is we use a network, just like we have here, but rather than these layers being fixed and arbitrary, the layers are actually going to be iterations of our algorithm. So this, basically the iteration of the algorithm is going to become a layer. Okay, we'll talk more about that in the next few slides. So we're using a network, but the layers in the network are coming from our iterative algorithm, and that's where the model or the structure is going to come into play. The second approach is kind of the opposite. So we end up using an algorithm, not a network. We're going to infer using an algorithm. So basically, we keep this algorithm, but anywhere in the algorithm that there's something that depends on something we don't know, like something about the model that we don't know, we learn only that particular block. Okay, so these are two different approaches, and we'll talk a little bit about when we'll use each one. I'm not going to go into technical details. Again, I don't know what the background of everyone is, but those of you interested more in the math, we have several reviews where you could see more of the math, and we also have two recent books, one focusing on communications and one focusing on medical, where we show various applications of these ideas as well. Okay, so a little bit more about unfolding. This actually goes back to a really beautiful paper, like a small conference paper of Gregor and Lacoon from 15 years ago, but it's been garnering a lot of interest and a lot of different extensions. So this is the basic idea of unfolding. So like we said before, we start with our iterative algorithm, and imagine that I take 10 fixed steps of this algorithm. Okay, so iterative algorithms, usually you run thousands of times to converge. But now I'm going to take a small number, like 10, and I'm saying 10 because usually that's what we use. Okay, the point is that it's a small number. I'm going to take 10 iterations of my algorithm. And now, again, if I just take an arbitrary algorithm, initialize it arbitrarily, and take 10 steps, I'm going to get a bad solution, right? After 10 steps, it doesn't really go anywhere. So this is where the learning comes in. So in the last part, what we're going to do is, rather than keeping these layers fixed, as they usually are in an iterative algorithm, we're going to free the parameters and learn them from data. Okay, I'm going to show an example soon, and then hopefully will be made more clear. But the idea is that we use the iterative algorithm, but then learn some of its parameters from data. And that's where the learned version comes in. Okay, now clearly this is going to give us something interpretable, right? We understand where the layers are coming from. But because it's learned, we can get very fast conversion with a small number of layers. And also, we don't have to know the parameters in advance. Okay, so that's kind of the first approach. The second approach that, like I said, was a more plug-in approach, is good for problems where we don't actually formulate our problem in a nice optimization framework. So this happens actually a lot in communications. One of the main areas where we've used this is in communications, because in communications, there's a lot of algorithms that people use, actually your phone uses all the time, that aren't really principal algorithms that are coming from some optimization solver, but they're rather very good heuristics that have been proven effective over time. So for example, one of the most well-known algorithms used in communication is the Viterbi algorithm, for those that are familiar with it. But without going into too much detail, basically it's a dynamic programming approach to solve the problem of detecting symbols that are sent over a known channel. Okay, so you do this dynamic programming approach that uses the likelihood of the symbols to recover the symbols. Again, without going into details, it's a super popular method. All of the phones use it. Here's Viterbi getting the Medal of Science from Bush, thanks to that algorithm and Qualcomm that was established based on this algorithm. But of course, it requires knowledge of the channel. Okay, now in today, where networks keep on evolving, knowing the channel, especially in wireless environments at any given moment in time, is not practical, right? And would require huge overhead. So this is a good example where we would use a plug-in approach. And basically what we do is we use the algorithm as is, but every time it's going to need something that depends on the model, we're just going to use a network for that particular block. So in the Viterbi case, the dynamic programming we could use just as it is, but every time we need to compute the likelihood, we'll use a very shallow network just to compute that likelihood. Okay, now that's a very, very simple solution, but surprisingly, it works very well. And we could show that it gives us the same performance essentially as Viterbi, even though Viterbi knowing the channel, even though we didn't know the channel, and it doesn't need any overhead, okay? Because it's a very shallow network, you could train on the fly. Okay, so those are kind of the two approaches that we're going to be using for model-based deep networks. And now in the rest of the time, I want to go through applications, but let me say in advance, I don't have to get through all of them, so I'm happy for people to ask questions, and you know, even if we don't get through all of them, I think hopefully it's more important that the idea is clear.
Go back to the unfolding. So there were two approaches.
Right, one was unfolding. Why is this? Yeah.
One is this thing.
Right, and the unfolding I'm going to explain more now.
You are going to explain.
Yeah. Yeah, no, I went through it quickly. I'm going to explain it now, but then if it's not,
The hybrid is
right, the hybrid is just easy, right? But if it's not clear now, then ask. Yes, that's what I'm going to explain now. Okay, so let me start with that, and then we could do this slowly, and I don't have to go through all the applications. It's more important to kind of get the main ideas. So let's go back to unfolding. That's kind of the more complicated one, but actually the one that we use more. So in a standard iterative algorithm, right, I have my input y, I have my iteration that, just to make things easy, let's say I did gradient descent, right? So I'm going to be computing the gradient and moving in the direction of the gradient, so that's the f. And then at every step, I get my estimated output, xk, right? So here I have f many, many times, and I keep on going. That's a standard iterative algorithm. Now what we're going to do in unfolding is that rather than this being fixed, we're going to parameterize it by parameters. And I'll show an example on the next slide, so hopefully that'll be made more clear. We're going to parameterize it and then learn these parameters. Okay, so I'm going to say in advance, let's say I have 10 layers, and I have, let's say, these 10 parameters, and I'm going to do training end to end to learn those parameters. Okay, so let's look at an example, and then if it's not clear, we'll spend some time discussing it. So one of the most popular methods today in signal and image processing is what's known as sparse recovery. So this is a very simple model. I assume I have an unknown x, but I'm going to assume it's sparse, meaning it has a small number of non-zero values. It's measured through a linear measurement system A that I assume I know, and we assume that we have Gaussian noise. Okay, so this is essentially like the simplest signal processing problem, and a very standard way to kind of estimate x is to set up a least squares problem. So I try to find the x that minimizes the squared norm plus an L1 regularizer to promote sparsity. Okay, so this is known as the Lasso problem. It's been studied super extensively, like tens of thousands of papers on this, but probably one of the most kind of used methods and earliest methods is due to Ingrid Dabouchies from 20 years ago, the ISTA, what's known as the ISTA algorithm, iterative shrinkage and thresholding. And this is really a projected gradient method, okay? So what ISTA does is at every iteration, you compute the gradient of this term, okay? So these two blocks are computing the gradient of the L2 square. And then there's a soft threshold, which is basically the projected gradient, that's the projection onto the L1 ball. Okay, so at every step you compute the gradient, that's these two green blocks, and then you threshold, soft threshold, which projects onto the L1 ball and promotes sparsity. Okay, so the ISTA method says, you know, start with an arbitrary X, do this 20,000 times, okay, with an appropriate step size, and you'll converge, because it's a convex problem, you'll converge to the true underlying sparse X. Okay, so is this clear? This is kind of a standard sparse recovery method. Okay, so how would we unfold it? So what we would do is we'll take this block, we'll write it down 10 times, okay? But now, instead of assuming everything is fixed, so mu is fixed, A is fixed, and lambda is fixed, we're gonna start freeing some parameters, okay? Now this is an art and a science, right? Because the science part is up into here, right? Until now, everything was very principled. Now comes the art, because I get to choose what I'm gonna free, right? So in the simplest case, I could keep everything the same and just learn the lambdas, right? So rather than saying I have a fixed soft thresholding operation, I'm going to learn the soft threshold and I'm going to let it be different in every step. Okay, so in a standard ISTA, it's the same lambda for all steps. I could do the same with mu, right? So that's the easiest approach, is to just learn the scalar parameters. Leave everything intact, learn the scalar parameters. Even that already brings a huge advantage. Of course, the more elaborate case would be that I learn these blocks. Okay, rather than keeping them fixed, I learn them. And here you could start asking questions like, well, if I know A, why would I want to learn it, et cetera, et cetera. So what we find in practice is a few things. First of all, there's a difference whether you really know A or you think you know A, right? If you really know A 100%, it comes from the physics, it's not going to budge. You could use it in two ways. A, you could just use A, okay, rather than making it arbitrary. What we find more effective is using it for initialization, but not keeping it fixed, okay? Of course, you could use the structure of A. So if you know that A, for example, is tuplets, then you'll use a convolutional net and not just an arbitrary net. So there's different ways to incorporate what you know, but still allowing for learning and not making it fixed. And the nice thing right away, as you can see just from this example, is that clearly the layers here are coming from the optimization solver. So they're interpretable and structured by definition. And if there's anything else that you know about the problem, right, you just add it to the optimization problem, it will automatically change your architecture. Okay, so there's a tight coupling here between the optimization and the network that you get. Yeah.
Learn, so there is a clear process here that leads to an approximation of every iteration, right? And so there, what is different?
Yeah, okay, good. So typically when you solve ISTA, you decide in advance what lambda is, okay? So you say, I'm gonna choose 0.5, and that's it. And it's not learned, it's fixed. When you iterate the algorithm, it's fixed, okay? When we say learn, what we're gonna do is we're gonna write this down. Let's say I have 10 layers, and now I'm gonna use training data and learn the lambda just like you would learn in an arbitrary network.
Training is produced with this function. Begin with.
Okay, so that's a really good point. So is the training, okay, so I was going to get to that later, but let me get to that now. Really good question. So where does the training data come from? So that's a nice thing about this approach, is that, first of all, we use the model in several ways. A, we use the model to generate the architecture itself. So here I'm talking about using the model to generate the architecture, right? Because this is coming from the model. Okay, the second part where I use the model is in the metric. So when I do the learning, I'm again going to use the model rather than just doing in standard learning, right? You would do x hat minus x, like the estimated x matching the training data that you have. But now, since I have a model, I could also add the y minus ax and x bars to the metric for learning. Okay, so I use the model to develop the architecture. I use the model in the metric for learning as well. And then the third thing is that if I believe in the model, if I think the model is good enough, I use it to generate training data. Okay, so I don't even have to have external, and we'll see examples later on, I don't have to have external training data, which, for example, in medical imaging I may not have. I use the model to generate training data. And even though it's not exact, it's still going to give me good learning power.
So it's like each one is a surrogate of the model?
Yes, yes. So it's like I'm reusing the model in several ways. And I think the surprising thing, and part of it we could prove, we'll see at the end, is that even though if the model was 100% exact, right, then I wouldn't use learning. Then I would just solve an optimization solver. So we know in advance the model is not exact, but even though it's not exact and we're kind of using it in those different points, it still leads to very good learning power. And we'll prove that and show examples later on when we see real data.
How is this different from physics informed?
Right. So in PIN, what they do is they use the model just for the metric. So they take right. Like they take a standard learning architecture, standard training data, and then the model is used instead of just x hat minus x, you would have x hat minus x plus the model equation. Right. So we do that too, but that's not what really gives the power is the architecture. Here,
power. It's like it maintains it's why it's kind of in between the two.
Right. So you have like on one hand model-based, like total model, no learning. On the other hand, you have total learning, right? And now I want to gradually go between them depending on how much training data I have, depending on how much I believe in the model, depending on the difficulty, right? Because at the end, if I'm Google and I have trillions and millions of images and I have all the compute power in the world, then I could just do black box deep learning, right? On the other hand, if I have no training data, I need 100% reliability. I'm like kind of at the other modeling extreme, then I'm not going to do any learning, right? But in real life, we're somewhere in between, right? And we want to be able to kind of gradually go between them, but in a way that I'm controlling how much learning I'm doing, okay? And that's also subjective, right? Because it depends on the application. So if the application is, is this a cat or a dog, then maybe I don't care about control, right? But if the application is I'm in a car and I don't want to run over a pedestrian, then I care a lot about control. Okay, so that's also something you want to be able to play with.
So this learns some biases as well. And so I wonder the similarity with ensembling, where you, does that make sense?
Yeah, no, continue. I like your question, yeah.
Because in ensembling, you assume that the model was kind of okay, even though that it wasn't quite
right.
You estimate the bias.
Yeah. So there's a lot of similar. Actually, we have a paper just on that where we're kind of looking at relationships to like you could show, at least in some simple settings, that this ultimately does that. It's like learning a bias in a controlled way. Yeah, so we did show that. We actually have a paper specifically on that, like connecting to, that's why I'm smiling, to connecting to like estimation theory. I think the reason why I like to present it this way and not through estimation is, estimation is like specific, right? You have to go through the statistics and the model and I love estimation, don't get me wrong. It's just harder to kind of set up, and it's usually specific to like Gaussian models or models that you could write more specifically. Here in this viewpoint, it's totally generic because I could use any optimization metric, I could use any optimization solver. It's just easier to set up and it's much more flexible. In special cases where I know where I could make the equivalence, like I could write down the Gaussian model, et cetera, then we show that it has that interpretation. But this is much more generic. Okay, but thank you. Yeah, those are great questions. Thanks.
Can I just one clarification? So the metric function that you talk about, that's like the loss function that machine learning talks about.
Yeah, okay, excellent question. So it's confusing because here, in principle, we have two different losses in principle because there's the loss function of the optimization, right? Which here, if I go back, would be this, okay? So this I'm using for the optimization and my architecture is gonna come from this. Now, at the end, once I have the architecture, once I do this, and let's say I decided I want to learn the lambdas. Now, I didn't show this here, but now I have an external learning function, right, to learn these parameters.
So you have different loss functions.
Right. Now, I can make them different. I can make them the same.
Yeah.
But I could also make them different. So what we do in practice is actually, okay, the question because now I could. So, for example, I could use this for unsupervised training because if I use this metric as my loss, then I don't need supervision. There's nothing supervised here. Okay, so if I don't have training data, then I could also make this my loss, and then I don't need training data. On the other hand, if I do have training data, then I would use this plus x hat minus x, match the training data. So they don't have to be the same. Like I could add a train component if I have it, but if I don't have it, I could just use this, and then I don't even need training data. So it's also easy to make it unsupervised or semi-supervised.
But it would make sense to me that if you have one loss function across all of them, so across both the lambdas, because here I can just parameterize lambda.
Right.
That I would perform better, because now I'm jointly learning the parameters.
Right. Which is why we use it. But if I have training data, I do want to add that. So I don't want to put the training data. You mean already over here when I'm getting the architecture? The architecture just wouldn't be affected by it because the data term isn't in it. So when I mean, I could put it in there, it just wouldn't affect the architecture. So the architecture is affected by the data term and by the regularizer. Okay.
The data here is X and Y, right?
So the data is Y. X is like the parameter that I'm trying to estimate.
Right. Yeah.
But it is confusing. It's confusing because if I'm doing so this isn't learning. This is just optimization. When I have supervised learning, I have like the X hat is my data,
yes.
right? Exactly. So that's I think the source of confusion because here X hat is the solution to the problem. So it's like right. So here I'm not looking at training data because it's not yet a learned version. If I have training data, then I use that in the loss function, but I don't use it here because this part is not assuming training.
So for you, supervises, I have X hat and Y, and unsupervises, I just have Y.
Right, exactly. But you are raising a very interesting point, which is right now, I'm looking at that as two separate processes, right? I'm saying in the optimization part, I for sure don't have X hat, I just have Y. You could ask the interesting question of suppose I wanted to accommodate for having training data in the optimization part of things, right? Which is not what we're doing now, but that's a really interesting question. So right now they're like two separate parts, but you're raising a really interesting point of, well, what if now that we have established that, what if we look at them combined? And that's very interesting. That's not what we're doing here.
So this is related to, as you know, there's a lot of work on ML for optimization. That how do you use ML to speed up optimization or whatever, and this has.
It's very related. Yes.
I've also heard people call it proxy optimization because.
Yeah, and we actually have some results on that I wasn't presenting here today, but you're all giving me opportunity to put in more things, so that's great. No, that's great. Yeah, we do also use that for that. So I could right here I'm talking about it as learning. But I could do the same thing and view it as I'm not trying to learn everything's exact. I know everything, but I want to have just 10 iterations, right? Instead of 20,000, I have 10. So I am speeding up at the end. And that's a really, really interesting point. Actually, when you think about it from an optimization perspective, it's a little bit magical, right? Because I'm saying everything's exact, everything. I have a solver. I know it will converge after 20,000 times, right? There's even theorems that say, like, from all first order methods, this has the fastest convergence, right? And now I could do it with learning, and I'm going to beat all of those bounds. So at the first thought, that's actually confusing. Like if I have a theorem that says from all first order methods, you get this in this order. Why is this doing better? And that's actually confused. Like we were confused about that, right? So the reason it's doing better is because we're actually cheating, not intentionally, but we're cheating because it's not, even though it's a first order method, it's not. What do I mean by that? Like I set it up as a gradient solver, so it looks like a first order method. But then when I do the learning, these parameters actually depend on Y's that were not part of my original formulation. So like the theorems actually this took us a while to kind of wrap our head around. So you have to go back to like how these theorems are proven, but they don't allow for training data, right? Like they have a single input Y, and then there's all these bounds saying from all first order methods, this way. But what if you have many Y's and many X's? That kind of doesn't fit into, right? So it's like you need a new theory of optimization that says, what if you have training data in optimization? It's just not the way optimization is set up. So what happens in practice is that you can actually beat those bounds using the training data. Yeah, that's really interesting.
So then the other question is, next slide. So when you are learning these different lambdas, do you look at the different lambdas to see if there are patterns?
You're all asking like all the perfect questions. Yeah. So okay, these are all like excellent questions for like PhD students that I'm looking for. So no, because this is something that we started. Yeah, right, exactly. So looking at the students here. No, but you're asking exactly like this is going through my research question. So this is so I'm just saying it like to everyone because I had a student who started looking at it, and then honestly, it's a hard problem, right? Like, so looking at even more generally, like these A's. So I would like to think, right, that let's say I have 10 layers, as the layers move forward, are they, actually as a question, are they converging to this when A is known, right? So the thing is, I'm not sure what I want the answer to be, right? Because on the one hand, you want to say yes, right? Like, yeah, I expect it to converge to this. On the other hand, I want to say no, because if it converged to that, it couldn't, because it needs 20,000 iterations to converge to that. So in some sense, if it's solving the problem in 10 iterations, it's probably converging to something totally different that, you know, we weren't smart enough to think of alone. We needed to run this algorithm to get to.
My intuition is that for this problem, given what lambda is, the regularizer, that initially I shouldn't regularize it too much, and toward the end,
it will converge, right? So what we could prove, and I have a result like that at the end, so we could prove that, let's say, going back to statistics, right? Because that's like the formulation we know to prove things. So we could prove, for example, like in the setting of product factors, where we know like the optimal thing is approximate message passing or whatever, we could show that if we don't assume we know the PDF, but there is an underlying factor graph PDF, and we do like unfolding to AMP, we will converge to the true AMP solution, okay? Which on the one hand is a really cool and important result, right? And that also goes back to what you were asking. The only caveat there, it looks like a really good result, right? But to be honest, there's a caveat, right? Because when you say converge, the whole point of unfolding is that I use a small number of iterations. So I don't want to converge. I want to say in 3 iterations, I get there, right? But none of these results are always asymptotic. So in practice, like we could prove that, which is satisfying. What we can show in practice is that when we simulate it, it happens pretty quickly. But I don't have a theorem that says it's going to happen in 3 iterations. That's kind of the gap, right? Yeah.
So when you're doing this learning, you don't say, and you have training data, you don't say that you're sampling the gradient in multiple places, and so you do like a market search to deal with that.
Yeah. So it's a little bit like that. And we see that when we prove the AMP result, right? Because again, this goes back to the question of like, if there's all these bounds that say, whether they're statistical bounds or optimization bounds that say, and there are bounds that say, this is as good as you can get, and we're doing better, right? So how are we doing better than the bounds if there's bounds? And the mathematical or statistical reason is because we're cheating, is because we have training data and these bounds were not formulated under the assumption of training data. Okay, so that's a formal answer. But the more intuitive answer is, okay, so I cheated, fine, but still, how's that benefiting me? Like, how is that training data benefiting me? And this is the point, right? The point is that training data, in a sense, is guiding me to a better local point quicker, okay? So that's what's happening. Proving that is hard, and we can only do that in very, very specific scenarios, but intuitively, that's what's going on. And that's where the training data is kind of helping me cheat.
So in the limit, to be practical, you only want 10 steps.
Exactly. But all the machinery I have to prove things, right? To prove things in the statistical sense don't allow me to prove things for a finite. And even in like sampling theory and compressed sensing, whatever, the results are always either up to a constant or asymptotic, right? Like we don't have those finite results that say in 3 iterations, boom, you got that, right?
And then the bounds that you're talking about, are they loose bounds or are they tight bounds? Like
no, so like optimization. No, so in optimization, the bounds are tight. It's just that they're, if you look carefully at like under the assumptions, right? They don't allow for training data because that's just not part of the formulation. Yeah, they're tight. They're just looking over a different subset of problems, so to speak. Okay, so I'll go through this quick. So another nice thing about optimization, besides all the things we said before, is that there's a huge machinery in optimization, right? Like people spent, decades developing different concepts in optimization. And now we could start looking at those concepts and just kind of taking them over to networks, right? So we could go through many, but just to give one, which I think is cool. So, a known challenge in networks is how do you make networks robust, right? Like what if the test data, what we call generalization error, right? Like what if the test data is different than the training data? And that's a known problem. And there's, thousands of papers and different heuristics that people do in order to do that. But now what we could do is, if this is all starting from an optimization problem, there's books on robust optimization theory. Okay, here's one by my colleagues at the Technion. And we could take that machinery and just use a robust optimization formulation, unfold a robust formulation, and then automatically we get a robust network without having to play around with heuristics. So this is just a simple example, going back to the least squares problem we had before. How people in robust optimization would treat it is they would say, okay, we don't exactly know A, we have A plus a perturbation, and then we also optimize the perturbation, and you could prove, again, this is well known, you can prove that that's equivalent to minimizing almost what we had before, but with an additional normalization, which again, you wouldn't just guess, right? It's a specific normalization that comes from optimization. And now all we have to do is compute the new gradient of that new problem, and you get this new network, which is very strange, right? It's not a network that you would guess, but it's all very principled. I'm not guessing anything here. And not surprisingly, of course, it performs much better than all competing methods that were based on heuristics. And this is super simple. Like, I'm not doing anything, right? You could do it in 5 minutes. Like, it's not like you have to sit there and start touring around. Okay, so hopefully that shows, let me just look at time. All right, I'll speed up. So how much time do I have?
You can talk for about 10 more minutes.
Okay. Okay. So that was the theory. I mean, most of it is application, so I'll go through really quickly. But I don't want it. Like, if you have questions, that's more important. So feel free to ask.
The X's and the Y's that you were showing, like how big in terms of cardinality, like how high dimensional are they in the problems you're looking at?
So okay, we could see applications, but it could be anything from a few parameters to three-dimensional images. So there's thousands of parameters, right? I mean, that's the beauty of it, that it's insensitive to all of that.
No, I understand that, but just to get
it could be anything. So let's say the first thing we looked at was images. So here the X would be, whatever, as many pixels as you have in the image, right? But we also look at problems where X are 3 parameters, right? So it depends. So the first application we looked at was, very standard image deblurring. So I won't go through the details in the interest of time, but basically we set up an optimization problem. We unroll it. Again, you end up getting something that you wouldn't guess. It doesn't look like any of the known networks that you know, but super principled. This was a paper from a few years ago, kind of the first time we worked on this more systematically. And the student who did it just did it on a laptop using MATLAB. Okay, so like, the sloppiest thing that you could think of. And
sloppy.
Well, sorry. MATLAB laptop is good, but I'm just saying today, like when people ask me for the code and I'm like, it's in MATLAB, they're like, what? It's in what? So, super simple. I mean, not simple to take away from the student. Super simple in a good way. Right, exactly. And you see that even with that, like, very simple idea, so our method is referred to as DUBLID, deep unrolling for blind deblurring. You could see here, these are standard databases that people use to compare results that we do much better than state-of-the-art, where these at the time at least were state-of-the-art networks with thousands of parameters, etc. Both in terms of quantitative measurements and visually, we get much better results. Sorry, I'm going through this quickly in the interest of time, but there we used a fixed regularizer, right? It's all based on like L1 sparsity. If we have more challenging problems, we can actually learn the regularizer. So together with unfolding the model, we unfold the regularizer. Here specifically, we learned normalizing flows, but now we've been doing the same thing with generative models, right? You just put that as part of the unfolding process. And of course, we could treat, this was already collaboration with Google, we could treat much more challenging problems. So we could look at very, very heavy noise, heavy blur, or just areas that are totally missing. And again, 10 layers of a simple optimization solver. We do much better than competing methods that are much, much heavier. Okay, moving to medical. So one of the problems that we've been looking at a lot are different problems in ultrasound. And one of the problems in ultrasound is blood flow. So when you're trying to recover blood flow. And what happens is that you get very, very strong reflection from the tissue. Okay, because the tissue is always there. You can't just see the blood. Okay, so what you see here is after separation. Really what you see is you see them both together. And of course, the tissue is so much stronger that you don't see the blood. Okay, so this is a problem for a long time. What people standardly use is like PCA, things like that. It doesn't do a very good job. So I'll skip the background. We set this up as an optimization problem where we assume that the blood is sparse, because it is. It just flows sparsely through the image. And that the tissue is low rank because the tissue doesn't vary from image to image. Okay, so we set this up as a low rank plus sparse problem. We use our favorite optimization solver. We unfold it. I'll skip through the details, but again, it follows the unfolding. And this is all real data. Okay, so 10 iterations of this unfolded method. This is all true data. This is what we start with, and we get really, really good separation. Now, the nice thing here, going back to all the questions before, is that there is no training data, right? Because anytime I measure a person, I'm going to get this together, okay? So when you look at this, you could say, well, how do you know you separated? Of course, we just know visually, okay? And there's different metrics that you can use. But you could see by just looking at it that it looks like it did a really good job, okay? But there is no ground truth. And the beauty is, this goes back to the questions before. We use the model to generate data. Everything is done. So there's no training data here. Nothing was given to us in advance from the doctor's perspective. They just gave us like one thing like this, right? And we gave them that, and that's it. Okay, everything else is offline based on the model.
And the parameter you from the 3 here is lambda.
No, so here we freed everything. Yeah, because here we know the model's a bad model. Okay, so modeling it like low rank and sparse, it's a human body. All this other stuff goes on, right? So we freed everything, but still, it's only 10 layers. So at the end, there's not a lot of parameters to learn.
This is done on a video, is that true?
Yeah. So an ultrasound scan is always a video. Yeah. Yeah.
So structurally, you know what from the tissue.
Right.
Speaking, right?
Yeah, so that's what we're doing. So we're saying the tissue shouldn't change, although that's not true because the person breathes, and that's what I'm saying. So it's like all very vague, but the mathematical modeling assumptions we make is that the tissue is low, like when we stack the tissue, it's low rank because the person supposedly is not moving too much, and the blood is sparse. But those are like very general assumptions, right? I can't really, we tried things that were more elaborate, like actually differential equations, whatever. It's just so bad in a regular scan because people are so unpredictable. Really, people do stupid things like breathing and moving. And we actually tried, like we did scans where we said, when we scanned, we said to the person, like, the worst thing you could tell a person when you're scanning them is not to move. Probability 1, they'll move more than if you told them not to move. No, it's actually the psychology. I know there's different, the psychology of that is so funny. Like you tell a person, okay, now don't move. They're all over the place, right? So like, and then we figured it's not practical. Like if I want people to be able to use it, you need to let the doctor do their thing, right? So we still use those assumptions, and that's the beauty of this unrolling, right? Because abstractly they're still correct, but practically they're not, and then the unrolling kind of compensates for that. Okay, so I think I'm really out of time. So I'll skip through this. I'll just say very high level what we did here. So Tina mentioned we've done, over 20 years, a lot of work on sensing and subnyquist sampling, et cetera. And all of that is nice and whatever. I'll skip through all this, but it assumes structure, right? Like the way we could get subnyquist is we assume something about the signal, which is usually fair. Like in a radar, we assume the signal is pulses. I mean, that's true. That's the engineering of radar. But still, you assume structure that you in more complicated, complex scenarios might not be 100% correct. So the nice thing is that now we could revisit all of those sampling results that we did and that have applications but have limitations, right? And now we could revisit them and extend them to much more general applications where we don't have to have those strong limitations. That's point number 1. Point 2 is the computational part, okay? So anytime you do compressed sensing or subnyquist or anything like that, there's still a computational cost. It's not huge, but it's still there. And if you're thinking about portable devices or edge devices or super low power devices, any cost is a cost. So now we could use unrolling twice, both to compensate for the fact that we could use more general problems that don't have to have the structure, and also that we could really do it on the edge in real time by doing this unrolling. So, okay, so I'll skip all the slides that get to that.
Sensing in a way.
Exactly. It's I would say low power, highly efficient compressed sensing without having to have those structural constraints. So let me just show one. Do I have time to show like one example? So let me turn. Okay, wait. I'll say what it is, and then I'll turn the video on because I can't put voice and talk at the same time. So here we're actually, this is a project that we're really excited about. So here we're working on a portable ultrasound device, like building. There's portable devices out there, but they have many limitations. They don't give high quality for many reasons that we won't go into. But basically what we want to do is build like a very small portable device where you have a dumb probe. It does nothing but convert the signal to bits, send the bits wherever, but they should be compressed enough that they could be sent to wherever, a phone or anything else. And then on the device, use advanced computing to get not only good images, but to get more information out of the data. Because today, the machine will just give you an image. It doesn't give you the actual data. So now using this compressed sensing together with unfolding, we could actually do it practically. So what I'm going to show next is, so this is a doctor, a cardiologist we've been working with. Okay, so here he's, sorry, I can't talk. Okay, sorry, there's a problem here with them. Anyways, I'll talk through it. So here, this is just for power purposes. The data is going from the probe, which you can't even see because it's small, directly to a local machine, to a remote machine via the cloud, and soon you'll see him scanning to a tablet, but it could have been a phone. So the cool thing here is that we only need a tiny small probe. We could do cardiac images is the hardest because the heart moves all the time. And still you could see that he's doing it in real time. You'll see him scanning first to an iPad, and you'll see that he's doing this all in real time. And the other really cool thing is that now this actually gives me the data, not just the image. So now we can use the data and use unfolding again to solve the wave equation. So this is interesting, right? Because ultrasound gives you images, although we all know the physics of ultrasound, right? It's wave propagation equations. The thing is that those equations are high dimensional differential equations that nobody wants to actually solve, right? And if you actually sit there and try to solve them, it takes days, you get trapped in local minima, so it's not a good way of doing imaging. But now that we use unfolding, we use it once to get the data efficiently, then we could take the data, solve these equations, this goes back as to using unfolding for optimization, and we could start mapping physical parameters, not just an image. So this is a good example where here's a standard ultrasound image, right? You can see there's something going on. There's some areas that may be suspicious for a tumor, but you can't localize it. Now, what we're plotting here is a map of the speed of sound, okay, which is a physical parameter. So we're taking the data, this compressed data, solving these differential equations, but not really. We're solving them with unfolding. And then we can map the speed of sound, and you see that this is the area where the speed of sound is different, and that's the area of the tumor, okay? So it's like, it's taking the same data, so to speak, but rather than looking at a standard image, you're looking at physical parameter images, which could give clinically very high value. This is another example we've been working on for detecting edema, which is a really challenging problem of finding fluids in tissue, and you can't do that today with ultrasound. And again, using only like 5 iterations, we can actually localize by looking at the physical parameters and solving these differential equations. So this is the type of stuff that gets us excited, but there's a lot of work, of course, to be done. I probably have to end. I should end. Okay, so just another domain where we're looking at this, again, using the same simple ideas, is vital sign monitoring with radar. So basically our goal is to put a radar here in the ceiling, localize all the people and get their vital signs. Surprisingly, you could write this all down as a sparse recovery problem, okay? Again, it's not exact, but good enough that with a few iterations of unrolling, you could localize the people, you could get rid of clutter like fans, etc., and find their parameters. We've done this also for spirometry, which is looking at lungs, the volume in lungs, which is very important, let's say, for asthmatic kids, definitely in COVID. Actually, this started from COVID. And we can also do this for moving people. So here we're showing like a person moving in a car, and still we could get their vital signs, which is a very challenging problem. Okay, so let me wrap up because I know I don't have time. We're looking at drug delivery systems. Anyway, the cool thing is that, and through the brain imaging, this is all based on, like, it looks like it's more complicated, but at the end, it's based on the same underlying principles. So the super resolution, for sure, I'll skip. I wasn't really planning on getting to all this, so. Okay, and some communication stuff, but that's less of interest. I'll just end by saying, do I have 1 minute? 1 minute, okay. So I won't go through the theoretical sides, but I just want to say they're there, okay, for people who care about theory. So it's like anything in learning, it's of course very hard to prove results, but actually the fact that this is structured learning makes it easier to prove. So we have some theoretical results, of course, for simplified networks that could prove all the things I said. So we can prove that we get better generalization error, that we need less training data. And this is the result I already referred to on AMP, that statistically, we actually converge to the true statistical solution. So wrapping up, what I tried to get across are some ideas of how we could combine signal processing algorithms with machine learning. We looked at a variety of different applications. There's theory in progress, but just from your questions, you see, and those all excellent questions. There's a lot of, I think, a lot of interesting open questions here, both from the statistical standpoint, from the optimization standpoint, definitely from the application standpoint. So we're very, very interested in collaborating and working on this further. Of course, all this work was done together with my students and mainly by my students, so I want to give them all credit. Of course, our many collaborators that we have the pleasure to work with, and happy to take any further questions. Thank you.
Questions for Yonina? I can start with one is and also online, if you have questions, raise your hand.
Oh, okay.
I'll keep track. One is I will ask for the slides.
Sure, no problem. Absolutely.
And I can send it to.
Yes, absolutely.
Since you went quickly through the theorems, I was interested in the Lipschitz one. Could you talk a little bit about that? Because that was about generalization.
The first one. Yeah. Mm-hmm. So okay, great. Yeah. So here we looked, again, the results are, of course, always for simplified networks, right? So here we looked at the basic Lista network, and we want to look at the generalization error. So there's two things we could show. One, and generalization is always bounds that are not tight, right? We know that. So we're kind of in the same world. So one interesting thing is that, of course, intuitively, if you have more layers, right, your generalization error should should decay. But there is, for general networks, there's no result showing that it decays with a number of layers. So first of all, for the structured networks, we can show that the generalization error decays with the number of layers, which is intuitive, but it's nice that we can actually formally prove that.
What is the relationship that it decays? Like, does it
exponentially? So again, it's what you observe empirically, but there's no proof for that. So for the structured case, we could prove that. And the second thing is that we could actually write down a bound. So it doesn't matter exactly what it is, but this, whatever, this is what it is. But we could compare that bound to the well-known bound for like the same number of layers in a standard network, and we can show that our bound is smaller than the equivalent bound in general. So of course these are bounds, right? But in terms of bounds, we can show that our bound is smaller than the bound of a standard network, and that it decays exponentially with a number of layers.
The bound depends on, I see the norm of the weights and this.
So there's an assumption, right? Like you assume, but it's the same. We looked at the same assumptions as the standard network, so we're under the same assumptions. Okay, so all the assumptions are taken from like the equivalent without the structure, and then of course it's going to depend on the lambda, right, the soft threshold that we use or that we start the optimization with. So that's a function of it. But if we choose it appropriately, then it's always going to be smaller than the equivalent bound for an equivalent network.
Other questions? Yes. Okay.
So thank you for your presentation.
Thanks.
So you did a little bit about MATLAB. So I'm kind of curious.
No. I'm old-fashioned. So the other way around. People in my generation, I hate like when I say that, it sounds so old, but I am old. So, I grew up on MATLAB, right? Not a Python or whatever. So to me, MATLAB is like, please give me MATLAB, right? That's what I know how to do. But students today are like, what? No, everything's coded in.
So I'm curious what languages you use and the time scale that
Yeah. Okay, that's a really good question. So first of all, it really does depend on the student, right? Nice to meet you. So the earlier works were all in MATLAB because again, like then everybody used MATLAB. Well, not everybody, but at least coming from signal processing. Okay. In terms of the projects today, so that's a really good question. So it depends on the project and what our constraints are. I mean, honestly, coming from signal processing, right? Like students in signal processing, still their preference is MATLAB in the sense that there's a lot of toolboxes in MATLAB. If you're looking at communication or radar or things like that, there's a lot of convenient toolboxes and things like that. So that's their starting point. And if we're not looking at something that necessarily has to be implemented in real time, then like, let's say the radar vital signs is all still MATLAB, okay? Because that's just the language that's natural for that. On the other hand, the more advanced imaging results that we're doing, all the quantitative physical maps, things like that are more advanced. Real time is important. The network is more involved, right? It's not just a simple sparse recovery problem. It's actually a differential equation that I'm enrolling. So the network is more involved. There we use Python. But I don't know that that's a crude, I think it's still largely a preference, but yeah.
So thank you for the talk. When you talk about unfolding, you have these different layers. So these different layers are trained on the same data, right?
Yeah.
So
or not, or if it's unsupervised, then but it's still essentially trained on the same data. Yeah.
So parameters that they're learning are also the same. It's just
okay. That's a really good question. Yeah. So there's two versions of this. It could be what we call, this is just the terminology, what we call tied or untied. Okay, so in tied, I tie together the parameters over layers, and that means that I'm making them fixed, that I'm making them the same over all layers. Okay, untied is when I allow them to be different. Now, as a rule of thumb, okay, generally speaking, untied is better, it gives it more power, okay? But there's exceptions. So first of all, it depends on the training data, okay? So if it's supervised and I have a very small amount of training data, then there could be an advantage to tied, right? Because I'm learning fewer parameters, and then if I tie them, I potentially could learn something better. The other thing is that sometimes the underlying layers have physical meaning. Like let's say they could represent an unknown channel that I also want to estimate. Like I also want to know that channel, not only to solve the problem, but on its own. So if I need that knowledge, then I need to tie, right? Otherwise, I'm going to get a different solution in every layer, and I'm not really getting a solution. So there's some cases where we tie because there's some other motivation to tying. But in principle, if like I don't have any restrictions, then untie is better. Like making them different in each layer is better. It gives it more power. Sure.
Thank you. So we are at time. Thank you again.
Okay, thank you. And again, there's so many good questions here. So really, I'm here and really happy to collaborate. So
Yes, so Yonina will be on the 10th floor, in the 10th floor conference room. So if you want to talk to her more.
or in general, I mean, I'm here like in general. So
She's in Boston. She is our.
right, not like here, but Northeastern here. So
Thank you.
thanks. And this building is so beautiful. I'm happy for excuses to come over. So
Wait until winter.
that is true. Good. So ask me quick before it gets too cold. ISEC? I don't know if that was like a good or a bad but yeah, people kind of know what where ISEC is, right? I think that's like, because everyone I say ISEC, they know. So. Oh, really? The truth is, it's a beautiful building, but I mean, but it's a beautiful building. But when I come here, I feel like more at home because Weitzman is like small and.
I said like X.
Like it's the building next to X, EXP.